So first, I'd like to introduce Dr. Paul Kocher. So he is the founder of side channel cryptanalysis. And in crypto 1996, he presented timing attacks, and which has been cited more than 1,700 times. And in 3 years at the crypto 1999, he presented differential power analysis, which was cited more than 3,200 times. And those opened the new frontiers of cryptographic research. And Dr. Paul Kocher founded Cryptography Research Inc. And he devoted to the development of the SSL and the TLS protocols, and which is now widely deployed in most of the web services. And he also developed DPA countermeasures, and which are now integrated over 100 billion licensed chips. And for his exceptional achievement, Dr. Kocher was elected to the US National Academy of Engineering in 2009 and became an IACR Fellow in 2018. And in 2019, he received the Marconi Prize for his contributions to SSL and TLS. And recently, in 2023, he was awarded the Lefton Prize for his pioneering work of side channel analysis. So today, Dr. Kocher will deliver a lecture titled "The Why and the Limits of Cryptography in Practice." So everyone, please join me in welcoming Dr. Paul Kocher.
Thank you very much. I'm just super happy to be here and really honored for the invitation. Thank you to the organizers of this and Sasaki-san for the nice introduction. It's just great to be in the country with the best vegetarian food in the world. So really great. So the sort of outline of this talk, I'm going to talk about sort of why I think cryptography is important. And this is kind of a story about me a little bit, but I think some of this may resonate with a lot of you as well. I'm then going to explore some of the challenges that really make it hard to use cryptography in practice and limit what we can do. And in doing that, I'm going to tie into various projects that I've worked on. But my ultimate goal here is to encourage folks to work on some of the challenges that are limiting cryptography's ability to live up to its potential. And if that doesn't work and you're still really interested in theory at the end, you can feel really sorry for all of the problems and buy me a beer. That's okay too. But really my goal is to focus on cryptography in practice. I'll talk kind of through this about some of the technical projects that I've worked on. The perspective that I'm coming from, though, is one of somebody who's run a company, written a lot of software, built systems, kind of worked in a very constrained environment in terms of what kinds of things will customers buy, what sorts of things succeed in the field. I've worked in kind of different kinds of organizations. Cryptography Research was a bootstrapped company. ValiCert was a typical venture-backed company. I've been a big supporter of the IACR. Currently, a lot of what I'm doing involves investing in startups and advising them and trying to help them navigate some of these challenges. Been on various committees, the US Forum on Cyber Resilience, for example, and so forth. I mentioned only the awards because I'm probably the least qualified presenter you're going to have in the entire conference. I have an undergraduate degree in biology, and I was going to be a veterinarian, and I got sidetracked into cryptography. But I'm coming from a fairly different perspective than somebody who might be going through a more typical program. There's sort of an idiom in English where you can refer to somebody as a jack of all trades and a master of none. So this is somebody who's kind of okay at lots of things, but isn't a really deep expert at anything. And this somewhat describes me. I tried to make a list of things where I think I've spent more than 1,000 hours of my life working on that subject. And while I put cryptography first, there's a bunch of other ones. And that served me well in some ways, but it also creates some challenges, and I'll talk about that through this presentation. So if I look at other fields, there's kind of a reason or an underlying goal behind them. So if you look at medicine, you could write it in different ways, but really the goal here is to make people's lives better by improving health. If we look at passenger aviation, we're trying to transport people safely. So for cryptography, so what is this why? And the way I came up with expressing this is we're here to make the world better by improving information security. Now, that requires minimizing bad outcomes. So in the case of medicine, it might be reducing the odds of mortality in surgery. In aviation, it might be reducing the odds that a plane will crash. For us, it's reducing the odds that an attacker is going to succeed. And to do this, we have some really just absolutely incredible tools. We have algorithms and proofs and countermeasures, engineering methods, all that are sort of here to help us try to achieve this goal. But again, for me, the goal of cryptography is the outcome. It's not the tools that get us there. It's not the process of getting there. It's delivering that outcome to a person who's trying to accomplish something. Now, the outcome is the end of a story. So I'm going to move backward a little bit, and we might sort of think of one of the stories that we tell in one of our papers. We might say that Alice is going to use her secret key K to compute some function F of the key and a message where, and then where would be an explanation of what the function is and what the properties of this function might be, what we can prove about it. But this here still is sort of the moment in the middle of a story. Now, it might be the most exciting moment if you're really into the algorithm, but if you're the end user, this is kind of just a small part of an overall picture. And so let's go back a bit before this happens. So we have here a user, I'm going to call her Alice, and she has a system. This is some hardware, some software, some infrastructure, and it was built by some engineering team. It was acquired probably by an organization that maybe Alice works for or is associated with that gave this to her. And there is trust in this system. So the people who are doing this are doing something that they're doing because they're confident this system will provide some kind of an outcome. So maybe transacting over an insecure channel. And every good story has an adversary, so let's assume one tries to attack this. And then the story ending has some probabilistic uncertainty to it. There's some chance that this adversary is thwarted, the trust was justified, the system was beneficial. There's some chance the adversary succeeds, the trust was misplaced, and the system in that case was harmful. In the other areas that I talked about, like aviation, if I get on an airplane, there's about 1 in 10 million chance approximately that plane's going to crash and I'll die as a result. If a healthy person goes and has anesthesia, there's about a 1 in 200,000 chance that that person is going to die because of complications of anesthesia. Now, the question here, though, is kind of what are these probabilities like for Alice? And in medicine and in aviation, we're looking at fairly small probabilities. But for us, in our world, for many systems, the odds aren't very good for Alice. And a lot of what I'm going to talk about here is what are the challenges involved in making those probabilities better. Now, there's a lot that I'm going to skip for now, and I'm going to come to a little bit later, like sort of who Alice is and what the threats are and what the organization is behind the system, who are the, all of these kinds of details. And I'll talk about this kind of in an indirect way at the very end of my presentation. So we have some kind of a picture here, and this is actually an AI-generated image, but it shows kind of a bright light shining there, illuminating a little bit of the ground. And this is kind of how I think of cryptography. When we look at this, we have our functions, our algorithms, and they shine very, very brightly. And the things that we can see from them, the 256-bit security that's claimed, the proofs of security, these are the things that are really easy to see. But for Alice, this is kind of a problem. And this is partly because of psychology. So bear with me a second here. So if I show you these two pictures of cars, and I say, okay, which one has a better engine? And our brains will assume that the thing we can see correlates to the things that we can't see. And I can pretty likely guess which car you're going to vote for as having the better engine. If you are really contrary and you say, well, I want the one on top, well, fine, you can go buy that. But the one on the bottom is clearly much more likely to have a better engine. So we can say, okay, there's a correlation here. There's a connection between the expected engine condition and the paint condition. And there's some scaling factor in between, but there's some kind of a approximately linear relationship between the expectation of the thing that we can't see and the thing that we can see. Now, what happens when we apply this to cryptography? So Alice has got a human here. You might assume that the expected cost to break the system is in some way proportional to the effort required for the known attack. And I think for a lot of you, if you think about this, you'll realize that your instincts are really badly deceiving you here. If you upgrade from AES 128 to 256, you haven't made a buffer overflow 2 to the 128 times more difficult to exploit. Although I did ask Google how many times harder to break our products that use AES 256 instead of 128, and it makes the same mistake that a lot of people do. And it says that it's exponentially harder to break the products that use AES 256. So if we ever have to fight the AEI overlords after they win the battle, at least when it comes to security, they're going to be making some of the same mistakes that we do. There was a line that I used earlier and kind of glossed over when describing the situation. But because of this trust, Alice is doing something that she wouldn't do. She's transacting over an insecure channel. And when you look at the ways that people use cryptography in practice, very often, almost always, maybe I could almost say always, the reasons people are using cryptographies are something that you want to do that's otherwise too unsafe. But by applying cryptography to the problem, you can get confidence that you can trust that you're going to get some kind of a better outcome. So therefore, it's okay to do this unsafe thing. But what this means is that if you put excessive trust into a system, you actually get a much worse outcome than if you had no system at all or you didn't put trust in it, because you've gone and changed your behavior because you had this confidence. And there are lots of examples through history. Maybe the most famous is if you can look back to World War II. The Germans had the Enigma machine. The US was using devices, among others, the M209 that I've shown here. They're both breakable. The M209's algorithms aren't particularly strong, even by 1940s standards. People knew how to break it. But the US didn't put a lot of trust in the system. It wasn't used for high-value communications. So there really weren't large consequences from having the insecurity because there was not excessive trust in the system. In contrast, Germany had excessive trust in the Enigma machine, which was the reason that it had such a great, breaking had such a great effect on the war. So when we go back to this kind of picture of the scene here, the story that we're telling, we have this function f, and its properties shine really, really brightly. And it's really hard to see anything else when you're looking at this picture here. But when you actually ask the question of, okay, what are the things that are going to impact the user of it, we have bugs. And we have also what I'm going to talk about a little later, sort of academically interesting vulnerabilities. But these are the things that shape the risk, not necessarily this bright function that we might have produced in our cryptography classes. So why are there so many bugs here? So we can kind of look at this with a very simple model. We can say, if I'm a person working on a system and I have n pieces to it, well, there are order n things that might go wrong there. There may be order n squared interactions between the components. I might have 1 over n time to look at each element. So as I get more elements, there are kind of more of them, and I have less ability to analyze them. And then we can ask, question of, okay, what's the chance that I've built a system that doesn't have some kind of catastrophic weakness? So if I make just a very simple model where I assume kind of things work independently of each other, I can take sort of 1 minus the defect rate, raise that to the number of defect opportunities, and I get some probability that I've built a system that doesn't have any defects in it. Now, if I take kind of the best software people have written, it's been well analyzed, probably the control software for the US space shuttle, and the estimate there was that there was about 1 defect per 10,000 lines of code. So if I say, okay, if I've got a system with this quality and 10,000 lines of code, what's the chance I have no defects? It's 0.9999 to the power 10,000, or about 1 over e, or about 37%. Now, this is just looking at lines of code. If we look at crypto systems, there's more than just the actual software. There's our algorithms, there's our protocols, there's our security proofs. And then with the security proofs, I want to also call out, there's all of that text and language connecting the security proof to the real world, which tends to include a great deal of wishful thinking. So you may find certain parts of this analysis are much higher risk than other parts of it. Our architectures, our hardware, user interfaces, all kinds of things here. Now, this is really depressing. This is the biggest challenge that we really face in our industry, because everything about this is really, really awful. 0.1 defects per 1,000 lines of code is really optimistic. Yes, not all defects are exploitable, but still, that's a really optimistic number. 10,000 lines of code isn't very much, and a 37% chance of success isn't very good. And you can also look at this from how does this scale? If you go up to 10 million lines of code, kind of a medium-sized project, the chance that you're at 0 defects here is 10 to the minus 434. And if anybody likes those odds, check me afterwards. We can do some gambling together. And also as you get your code better, your quality improvements get harder. And I'm just talking about bugs here. We're not even talking about malice and backdoors and all of that kind of thing. And yet, so despite this being kind of a dismal picture here, this is actually an argument for cryptography. And let me explain why. So the most successful use cases of cryptography are things that remove vastly more complexity risk than they add. So if we look at sort of the most common places where ordinary users encounter cryptography in ways that kind of really do work in the field, it's things like SSL, TLS in browsers, SSH, and encrypted messaging, code signing, encrypted storage and backups, payment smart cards, things like this. And in each of these cases, if you look at the system, actually the cryptography does add a lot of security critical complexity. You've got your software, your algorithms, your certification authorities, and that kind of thing. But what you've taken away, for example, the entire internet's kind of communication infrastructure is just so much more. Now, in contrast, there are other crypto systems people propose, and I don't think I should probably name names, but that add things and don't remove anything. And those generally don't do very well in terms of getting uptake for partly this very reason. This argument is also a somewhat nuanced argument for using things like formal methods and proofs of security, because these also introduce a great deal of complexity. You have your proof system, your tools, your proofs, your mapping assumptions, all of these things. But they reduce defect rates, but also maybe they're simpler than protocol design. But the nuance here is, of course, that the added complexity, we can sort of look at it and say, okay, we've reduced the likelihood of problems. And you could say, well, this extra complexity is risk-free, but that would only be true if behavior was fixed. But as we talked about earlier, our hypothetical Alice goes and does something different because she has trust in a system. And if we make a proof that says that a system is provably secure, but it ends up ultimately being that the overall system is weak and change behavior, we've done more harm than good at that situation. So kind of rewinding kind of back way early in my career, go back to 1995, which I know a lot of you weren't even born then. This was, SSL2 was a broken protocol. It was undermining trust in the web. And Tahir Al-Gamal was the chief scientist at Netscape. And he basically pulled three of us together and said, OK, go fix this. And you might think, a protocol like this is going to have a huge team of people who know all experts in cryptography working on it. But actually, it was Phil Carlton who knew probably more than anybody ever met about sort of TCP/IP and networking and software development. Alan Fryer, who knew kind of the standardization process, and I was the only person who'd kind of worked in crypto and security on this kind of crash project to go redesign a protocol. And we sat down, we figured out some goals. We wanted the best possible security common to a client and server. So this was the era where you couldn't export cryptography with larger than 40-bit keys. So you might well have scenarios where a server could support stronger crypto, but a client only supported 40 bits and vice versa. And you wanted to be able to kind of negotiate the strongest possible combination. We wanted a smooth transition from SSL2, and that necessitated some ugliness. If anybody here believes in the afterlife, you probably can imagine what's going to happen to me for some of the things that I did in that protocol for that reason. Had to be efficient, but not at the cost of security, so compute, bandwidth, round trips. And one of the things that was, in retrospect, super important was to keep it as simple as practical. So that protocol was, I think, 27 pages of kind of main text, and then about the same amount in the appendices. I remember there was a kind of a competing protocol at the time called SET that was designed to do transactions securely. And I remember sort of sending it to the laser printer and having to reload the paper and ended up with this stack of more than, I think, 1,000 pages coming out. And I sat down to try to read it and kind of got a little bit through it and then forgot what was going on and went back. And it was just too complex. There was no chance that protocol could ever really be understood. And one of the goals here was to have a protocol that you could understand and reason about. And then the last one was the ability to adapt and evolve. And we now call this crypto agility, although there's kind of different aspects of that notion. This was the pre-AES era, so it was clear that that was going to be needed. I knew that RC4 was problematic in its key setup. I knew the other ciphers that were available, just none of them were particularly felt good. So I thought that we're going to have to put some new algorithms in. But if I look at kind of what happened, that actually ended up being maybe the most important part of the design. And that actually worked surprisingly well in retrospect. One other little notice, the team of three here was kind of interesting. The three of us didn't have really any common background. And I've worked with quite a few computer security startups. And one of the things that a lot of organizations struggle with is you get 5 people who can all do one thing really well, but nobody else can do the other things very well. And then a task comes along and either all 5 want to do it or nobody can do it. And I remember learning very consciously in this process how important it was to have complementary skills rather than overlapping skills when you're putting a team together to do something. So the spec, I think we released it in March '96. I remember thinking, OK, SSL2 is going to be gone pretty fast. That was just a quick transition problem that we had to solve. I was pretty confident that there were no issues except for the documented stuff, like 40-bit keys everybody knows are bad, but that's very well stated in there. And that if there were any oversights, there were lots of companies that were using this, people would be paying attention to it, and they would be caught pretty quickly. And I was kind of wrong on all counts here. So first of all, got this really painful lesson that basically old crypto never dies, especially if backward compatibility is seamless. There are probably still people who are using SSL2 today. The second one is actually kind of interesting. I mean, I felt really confident that this was a strong protocol, but when you're designing something, it's very, very easy to be overconfident because you spend all this time working on something, every issue you know about, you've addressed. And you talk to people, and they say, okay, you've solved all the problems that we can think of. And yet this thing that you don't know is the thing that's the problem that's going to come along later. And some of the issues took surprisingly long to be uncovered. So, if you asked me the question, am I confident that there are going to be no more discoveries about SSL3? I really couldn't say yes to that even today. So the spec came out, there was this IATF standardization process. It was really quite political, but still also very important and kind of enjoyable. And looking back at that, there's this question of whether Microsoft and Netscape would go in different directions for security in the web. And they ended up agreeing on a common protocol that effectively was SSL3 with the name changed. And part of what really struck me about that was that there's just lots of awesome people in the cryptography and security world. And that people really do want to do the right thing. And those relationships were the thing that made that happen here. So that was just really fun to see. A little less fun was the realization that, this 20-some page protocol was pushing the limits of the maximum complexity that we can cope with. And that's even ignoring implementations. And I'm not going to go into the various implementation bugs that have affected SSL implementations, but all of us know about Heartbleed and so forth. So if I step back here and kind of imagine the potential universe of cryptography, there's some kind of huge unknown space of what the potential is of what we can do. And then the potential of the things that we know about has been growing. And actually, right now, we're at a period of just really rapid expansion of what that frontier is. Maybe growing faster than any other time, with possibly the exception of the discovery of public key cryptography. So what's possible to do then, getting to be this very, very large space. But if you ask me the question of kind of to apply a filter to this and say, what are the things that you can actually make useful? And by useful, I mean, beneficial for real users after factoring in things like the risks of making mistakes. So if I go to this hypothetical Alice and say, here's 10 million lines of buggy software, why don't you go do something that you really care about with that? I'm not being beneficial to Alice. That's not a beneficial use case. So if you ask me kind of what do I get out of this kind of world in terms of things that I personally know how to build, I get this little tiny green dot here. And I made it kind of fuzzy because there are questions like kind of what's my budget and who am I working with. And I drew it right on the edge of known techniques because every system that I've worked on of any kind of complexity has required some innovation of finding new things that weren't in that sort of world of things that people have thought about from a research perspective, because there are unique problems there, and also because a lot of the research really isn't directed to the questions of what do you run into in practice when you're trying to use cryptography. This is not a unique problem to cryptography. The airplane that I took coming over here didn't remotely begin to approach the possibility of what people could do with airplanes. It was pretty much the same in terms of what you might have found on an airplane 30 or 40 years ago. So there's the fact that these complexity and safety challenges limit us is something that other fields grapple with as well. So I drew this sort of green dot of the things that I could successfully build. I'm going to draw a slightly different dot here, which is the systems that I think I could build. And those may be slightly misaligned. And there's an additional filter that I'm used to kind of applying onto this as somebody who's been an entrepreneur, which is kind of what's profitable, what's going to work in the market, what's going to be effective as a product. And that further constrains these already very small dots. Now, you're probably thinking, or you should be thinking, okay, here's this guy speaking to me. He doesn't even have a degree in cryptography. He was going to be a veterinarian and get off in the wrong direction. And he thinks he can build useful stuff. Is he being totally overconfident? And I might be. I actually don't know. I drew my circles as mostly overlapping. And that might be just a huge bit of hubris. And I made my green circle with an area that's greater than 0. And that could be wrong too. There could be math reasons, P equals NP or something like that. But there also may just be that I'm just not as good an engineer as I think I am. And I also didn't draw something giant and red where I think I can do almost anything. But to me now, the question, what is the purpose of research? If we go back to the goal that I talked about earlier of making the world better, research results are useful when they expand and align these circles. So if I can get my red circle to more overlap with my green circle, or if my green circle gets bigger, because I can now do things that I couldn't do that are now useful for end users. That's where we get to have the impact that matters. So the thought exercise I'm going to give you here, and I'm going to have two during this presentation, is let's define kind of a pretty modest security level. We're going to say 50% chance that the system, or better, that if a handful of smart people spend a year trying to analyze it, that they're not going to find an exploitable weakness. So that's a pretty modest goal. So I want to challenge you to think about, okay, what do your circles look like? And then the next piece is, what innovations would improve these outcomes? Because as you start thinking, okay, I really have to go do something, and there's real skin in the game here. I'm going to lose my salary for the next 5 years if I screw up. I'm going to put somebody's life in danger if I screw up. What can I do? You're going to start feeling first a little overwhelmed, then you start saying, okay, I'm going to start building this, and you start thinking about the things that you'll do, and you're going to run into problems. And I want you to challenge you to think about those problems, because those are going to be really interesting research topics. Now, from a business perspective, I drew that big red circle and said mine wasn't there, but my view of kind of a lot of that happens in the cryptography universe is there's a lot of teams that are operating outside of their success circles. And I've always kind of used that as the kind of fundamental force driving cryptography research and kind of how I bootstrap the company, and particularly was with security evaluations. So if somebody is going and building something where they don't really know if they're succeeding or failing, and you do a security evaluation of their work, you have a pretty good likelihood of finding something that's gone wrong that you can then report back and make your client happy, and they'll pay you for more of those. I found that it was most fun and often best to be doing evaluations for the companies that were using systems. If you work for a vendor, they often would want basically an endorsement and weren't really interested in hearing the bad news. But if you're you're the relying party, you're going to suffer the losses if something fails. You want to know what those risks are, so you're really well aligned. Vendors also would have more IP complexities. I didn't just do companies using systems, but found that was a lot better. So I've done probably several hundred security evaluations over many years, but certainly over 100, and very, very consistently found issues. So when you go back to this question of, okay, how are products doing for this hypothetical Alice? Again, the odds are not good. If somebody who's smart and determined spends a bit of time doing an evaluation, will consistently find problems. Some of the places to focus, if any of you kind of want to follow in this process, looking kind of at the periphery of the cryptography often worked really well. I would start by looking at the specifications or the design of a system, and kind of from that, there'd be places where you'd see that there are omissions and errors, and that's always a place to drill down. Like if somebody says that it's secure because of X and X isn't true, there's almost certainly something under the covers there. A slightly more depressing thing is that you look at the parts where it's solid. Somebody's got a really good proof of security around some aspect of a system. That just simply tells you don't look there. And there's plenty of territory to look in. So it didn't necessarily result in a better outcome. In fact, it just meant that I could allocate resources more effectively to the parts that were more likely to be soft. There are other places, sort of gaps between marketing claims and algorithms and so forth. And I'll talk about side channels in the next couple slides, but those were also an area that were very fruitful for analysis. So this process for me kind of led to credibility and relationships. And one of the nice things about Silicon Valley is people change jobs a lot. So I'd work with somebody at one company, 6 months later, they'd be at another company, and they'd bring me in to go do some more work. So that worked really nicely. And obviously, evaluation projects would also lead to projects to try to fix some of the problems that came along. And just getting paid to learn stuff was super great. You'd learn the technologies, the markets, the people, the challenges, what the attackers are doing, that kind of thing. Now, the findings here at some level are not surprising. The idea that you take some really complicated system produced by people under a really tight time schedule, the probability of there being bugs was already, I could have told you before I started almost any of these evaluations, it was very close to 100%. And saying, okay, you had a 99.999% chance that there was a bug here, and then I found one, and now you're at 100%, doesn't really change a whole lot. Although, if you actually look at it from the customer perspective, it makes a pretty big difference, because suddenly they have risk insights, so they're no longer putting the same trust in a system. And it also levels the relationship with the vendor. So the vendor, instead of saying, here's the system, trust me, is now in a relationship where they've said, okay, here's a system, trust me. The customer has come back and said, no, here's actually some evidence that I shouldn't trust you completely. Let's have a more honest conversation about what the risk profile of this kind of a system should be. All right, I'm going to do a kind of a quick detour. I've got to talk about side channels a bit here, because if I don't, you're going to ask for your money back. And then I'm going to try to relate that to this question of abstractions and how those fit into security. Also, kind of rewinding and going back in history, I spent a lot of time with computers. I knew that computation times varied. Large-scale things, hardware, properties, algorithms, sizes of inputs. Small-scale things like cache hits, handling of carries, multiply instruction properties, that kind of thing. And I was trying to implement linear cryptanalysis, and it really wasn't a lot of fun because the amount of data that you need gets to be really big if the biases are very small. And you look at the speed of your computer that you can have if you're a student with student loans and no money, and the amount of data you need to get the biases that you can find. It's kind of frustrating. And so I sat down and said, okay, there's some better data that I can work with here. And I realized that timing correlations within a block cipher were much better correlations to the things that I could get from the algorithm. And also realized the same kind of, from there realized that things like RSA were also really quite practical to analyze. So I wrote up a paper, and I'm probably going to convince you at the end of this that I'm just the most naive person in the world. I was thinking, okay, we're going to do this. People are going to figure it out. They'll solve it pretty quickly once people kind of know what to look at there. And you all know what happened. I think I'm not sure how many timing papers are mentioned. They've been making it. Timing mentions have been at this conference. One other kind of comment. People were super friendly about the paper, but there was one person who said to me, this is really more an engineering paper than a cryptography paper. And it's really fun to see that the borders of what is cryptography have expanded a lot over the years. And I really hope those will continue to expand. In addition to the sort of the academic piece of this, I was also using timing attacks a lot to break things because it was much easier than analyzing software. And a lot of the breaks there, some of them were cryptographic implementations, but a lot of them were comparison checks. And I remember one in particular where there was a smart card and it had a EEPROM write where there was a failure counter that would limit you to a few tries on a transaction. But the way the EEPROM function worked is it would first clear out the memory area and then write the new value in. So if you interrupted at the right point in time, it would zero the counter. And then I could use timing to see how many bytes matched correctly because it was comparing an input from the outside against the correct value. And the cryptographer who designed this was really annoyed. He said I was kind of cheating because I hadn't broken the system the way that I was supposed to. And this is, again, kind of this question of outcomes versus the tools and things. From a tool perspective, okay, the cryptography was theoretically sound. But if your outcome is that your smart card is broken, that's really what matters to the end user. A few years later, so I knew that power consumption varied, large-scale variations, small-scale variations. Bought a cheap oscilloscope. It was a cathode ray tube one. Thankfully, those don't exist anymore. Simple power analysis was just immediately obvious and which even easier than timing. Bought a digital oscilloscope, had the differential power analysis working. At that point, the evaluations were actually too easy. It was kind of a business problem because you were breaking things so fast and often billing by the hour that it wasn't actually great for business. But we filed a bunch of countermeasure patents and had a big saga connected to what we would sort of now call an embargo. So you had lots of devices in the field that couldn't be updated. It was really unclear if and how to ethically disclose. In this case, it got resolved by accident because one of the companies we were working with had an Australian executive who answered a question from a reporter thinking they were asking about power analysis and they weren't, and gave the story about what to say if a reporter asked, and story came out. But this question around what do you do with hardware vulnerabilities and responsible disclosure still is a giant mess. If anybody has a solution to some of those problems, we need one. Paper Crypto 99. And the TLDR here, I think most of you know side channel attacks pretty well, but basically the message to come from all of this is there's absolutely any information, no matter how tiny the correlations are, that you can pick up from the inside of an algorithm using power, timing, electromagnetic radiation, gravity probes, whatever it is, you're going to end up being able to break the cryptography. Fast forward again just a few years ago, I was at a conference and Mike Hamburg, who's one of the folks that was on my team at Cryptography Research, asked me this just really great question. He asked me whether there were security risks with speculative execution. And I started thinking, okay, maybe you can speculatively do an extra round of AES. And then by a really great stroke of luck, the next session was really boring. And I sat there and started thinking about this problem and realized that it wasn't a crypto issue. But so by the way, if any of you are just totally bored and you come up with a great result, that's a huge success for this talk. But you don't need to cite me in the paper. So I came up with Spectre. And then again, big saga with the embargo, kicked it with the Meltdown folks. There's also a researcher at Google who discovered the same thing somewhat before independently, had a paper. But now, these three attacks are kind of interesting because they cross abstraction boundaries. So we're used to kind of thinking of things in abstractions, like if I'm a programmer and I want to save some information to a file, I'll call fopen and fwrite maybe, and I don't have to understand how a file system works or all of the things that happen behind the scenes. In fact, what actually happens when you write to a file has so many mind-bogglingly complicated variations that you probably can't begin to reason about those, but you have this mental model of what's going to happen, and that's good enough to be able to make your program work. But here we have vulnerabilities that are sort of breaking down these barriers where you have different people working on different things. And this is a kind of a challenge because you couldn't build modern technology without abstraction. It's just this absolutely essential tool. It lets us deal with complexity. It lets domain experts focus on the separate components. And even though these abstractions aren't perfect, they're pretty effective. And when they're not perfect, it's kind of outside the security context. Excuse me, people call them leaky abstractions. So you have things like, a latency problem in TCP/IP, and Nagel's algorithm is causing this to happen. And usually these could waste your afternoon, and then you figure it out, and you understand the details of some abstraction that you're relying on, and you resolve the issue. Now, the situation with security is a lot more problematic. And one is that the simple interface tends to conceal security critical details and assumptions. You also have this problem of complexity bloat. So I was talking earlier about kind of as you build systems that are more complicated, this chance that you've gotten all the bugs out starts to just exponentially decay on you. And if you take something as complicated as, for example, all of the software behind doing fopen and fwrite and say, okay, what can you reason about the security properties of this? You're going to have a really, really hard time about that. And then complexity also hides vulnerabilities. One of the reasons is those that I kind of hinted at in the last slide, there was this siloing of expertise. So you put the domain experts onto each area. You have the experts who know microprocessors, and you have the experts who know file systems, and the experts who know cryptography. And these are different people, different companies, different teams, different acronyms, different conferences, email lists, code bases, tools, metrics, journals, objectives. Even the question of values varies between different groups. And kind of give an example of this, the CEO of ARM, when Spectre came out, very smart guy, Simon Segars, and he was quoted as saying, somebody whose mind is sufficiently warped towards thinking about security threats may find other ways to exploit systems that had otherwise been considered completely safe. So his values here are kind of implying that, okay, a warped person has taken the safe thing and made it unsafe by finding the vulnerability in it. And so again, so different worlds that aren't overlapping very well. In fact, you can kind of imagine different worlds. Like there's the world, going back to when I wrote the timing attack paper, there was kind of the world of people who would think about microprocessor timing effects, people who were writing fast cryptography, the engineer whose job was to go write that fast DES implementation or RSA, and then the people who were thinking about cryptanalysis. And there really wasn't kind of full intersections between these. And then you add, something like DPA, and you add kind of another little circle in there of, people who buy oscilloscopes for fun, and you get these kind of little small circles that don't have very many people or very much time being dedicated to the intersections. I put normal people up in the corner there too. So, but for me though, this is a problem, and a problem is an opportunity. So the opportunity here is that you have these spaces where there's not a lot of people looking, and I think there's a lot more interesting results to be found at looking at domain intersections rather than trying to really go deep into a single domain. And this is, again, a little bit of my kind of jack of all trades background, where I'm not the best at any of the things that I've worked on. If you look at something like Spectre or side channel analysis, other people have just gone so much deeper on those than I have. But the ability to connect different areas where people weren't making some of these connections still has an important, there's interesting things to find. And there's also a lot less competition for good results. Because if you think about the number of people who are really good at a particular mathematical technique, you've got a pretty big learning curve to get to be better than them. But if you go take, an area like aviation and cryptography and put them together, you may find that the intersection of people who have knowledge about both is 0 or 1 total in the world. And the chance that you'll find something interesting in that intersection is a lot higher. This siloing also complicates or completely prevents problems from getting fixed as well. So if you look at CPU architectures and timing attacks, I think we've had negative progress since the timing attack paper was published. And there's a couple of sort of reasons for this, partly one where the CPU architects are compensated based on their ability to come up with making things faster and not more secure. So there's kind of a value system and a set of metrics and a set of focus there that makes them want to maintain as much flexibility for optimizations in the future, which therefore means that making guarantees saying, for example, that the best case, the worst case, and the average case are all going to have the same timing limits your ability to do optimization. And if you look at a problem like memory safety, this has been an understood problem for years and years and years. It crosses abstraction boundaries. But the people who are responsible for maintaining legacy code bases in C may have very different incentives than people who are trying to make systems that are actually secure. When I described or painted the picture that involves Alice earlier, I put bugs and then I put academically interesting vulnerabilities as kind of one of the categories of things. And these three are academically interesting vulnerabilities, and they're interesting because kind of everything is working correctly. Like Inspector, the speculative execution engine, and the cache, and so forth, are all doing the things that they're supposed to do, but yet the composition of these pieces doesn't provide the security characteristics that you might kind of have expected. And so like for just those three papers, at least Google Scholar says there's like 21,000 citations to them. But in contrast, if you're Alice, what you care about is whether your system's breakable. And something like Spectre that really probably is never the easiest way to break into something is irrelevant, whereas that buffer overflow and some routine boring piece of software really is a big deal. So when I go back and look at the uninteresting bugs that I've been involved with that never became papers, many of these also cross layers of abstraction in very similar ways. You have somebody making an assumption about something which turns out to not be quite right. And these are the things that caused most of the bad outcomes. Earlier on, I gave you kind of the thought exercise to ask you kind of to think about what is in your red circle. What are the things that at least you think where you could go build a system that would be useful and beneficial for end users and solve some kind of a problem for them without creating more risks than it mitigates. So I'm going to talk to you about kind of the properties of mine. These are all kind of large amorphous subjects, so I'm going to go through them fairly quickly, but kind of my goal with this is to describe to you both some of the challenges as well as places that might be interesting to drill into if you're looking for problems to work on. At the very highest level, there are kind of four strategies, and these are extremely obvious. Reducing complexity, collapsing abstractions, reducing defect rates, and being able to survive and manage defects. And I'll talk about each of these in a little bit of detail. So reducing complexity, I mean, the first one of them, it's really easy on paper, just put fewer features in, avoid anything you don't need. In practice, this is really hard to do. But if I look at the successful hardware projects I've worked on, for example, they mostly just do one or two or three things, or there's one thing it does in the field and then some extra logic involved in programming keys in the factory or setting up things or testing. But trying to keep that complexity out and figuring out what's absolutely essential and what's just nice to have is a necessary and painful part of the process. And often that means accepting not only less features, it can be less flexibility or less speed. So you might be having to really understand, okay, what's exactly the transaction that you have to do right at the beginning of an engineering project rather than being able to make adjustments as you go along. For hardware projects, there's an upside of this, though, which is if you say that complexity is the enemy, you're going to make sure that your hardware is small. And small hardware is cheap to manufacture, which means that when you've got something that can be put onto a big chip and it's very small, lots and lots of people can use it and deploy it. And that's one of the reasons that the hardware cores that my team built are in just so many different kinds of chips, from cell phone chips to pay TV chips to big media processors, all kinds of things, because they're small and cheap to put in. One implication of this, or kind of one thing that I want to talk about just a little bit, is this question of kind of where should you run computations that you care about. And I'm here arguing for this idea that you really minimize complexity, get everything out of that sort of trust perimeter. But if I look at the projects that have been deployed and smart people have put a great deal of effort into, in many ways, I'm in the minority here. If you look at initiatives like Intel's SGX or TrustZone, or this idea that you kind of take a TPM chip plus the whole system of a PC and you put those together and try to get some security properties from that, the trusted environments there are extremely complicated. And I'm personally skeptical that any of those things are ever going to work. If you ask the question of, okay, here's a PC with a TPM in it, go spend a few months trying to find a way to get, circumvent somebody's security properties in there, I'll bet you I'm going to be able to do that. I don't have confidence of being able to deliver an outcome that I would feel good about just because of this complexity problem. And some of these, like Intel SGX, you can kind of see there have been problem after problem. Now, this high-level view doesn't tell you exactly what the problems are going to be. It just tells you that there's a high likelihood, given how big this territory of or space of possible issues is, that there are very likely to be some. Collapsing and minimizing abstractions. So, the first thing here is when you get these just giant software libraries that provide you a very easy to use abstraction interface, and whether it's, an operating system like Linux or the, POSIX libraries or, whatever it might be, these big things inherently have bugs. I mean, every person in this room knows that there's essentially zero probability that all of the bugs are currently out of Linux. And you can say, okay, in 10 years from now, will all of the bugs be out of Linux? The answer is still going to be no. And so when you have these big libraries, you have bugs. Often they're written in memory unsafe languages, which means that any memory safety issue anywhere in this entire surface area is catastrophic for the entire application. Now, one big advantage of hardware is that you kind of get rid of almost all of these lower layers. There's a few things like the transistor physics of the and the properties of the cell library that you're working with from the foundry, but there's almost nothing outside your control relative to what you would have if you were dealing with something like, a Linux PC in terms of the processor, the memory, all of this stuff. But even when you go to something where you might think, okay, hardware is pretty easy, we're going to make a little core, it's just going to do AES for the key that's saved on board, and there'll be no other function besides that. It turns out there's still just this big range of hidden pitfalls, each of which requires you to basically not be able to use the benefits of abstraction. I'll give you just one example here. Like, say I want to store a secret key on a chip. Got an AES key, I want to put it there. We're even going to ignore how it got stored in the beginning. Just what's the chip design piece? What's the place I'm going to put this? And you start kind of digging into looking what your options are, and you discover maybe you have available a fuse array that's developed by somebody that you can put on your chip. And you start saying, okay, well, there's error correction there. What are the security implications of this error correction? There's a debug mode, because you can't put something on a chip unless you can test that it was manufactured correctly. What are the security implications of the debug mode? What are the changes that are going to occur over time for yield? Because the job of the foundry is to make the highest number of good die possible for the lowest cost. So what you make for the first chip, where the yield is 90%, may not work the same as after some changes have been made that make your yield 95 or 99%. You've got things like side channels during burn. So you've got a fairly some kind of permanent change happening to the hardware as a bit is burned in that. And if you think you're going to go write your keys and save them in some kind of an untrusted environment, or that you're going to have the chip generate its keys internally and have them never leave, well, if you want to make sure those keys never leave, you better really understand the properties of what happens electrically when that burn happens. You look at these things, and a lot of them have various degrees of read destructivity. An FERAM destroys your data when you read from it, yet you can rewrite it, and then it becomes persistent. Or the fuse arrays on a lot of chips, you have a maximum number of seconds or minutes or hours over the entire chip lifespan that you're allowed to spend reading that, or you end up with a denial of service kind of scenario. So all these are kinds of things where you might think you have some block that you can just drop in and use it and you'll be good, but you actually have to throw away that concept of abstraction and really dig into it. And this is hard. And when you're working on a device, there's this kind of, or on a project, there's this fog, because you don't know if the information you're getting really is correct. You may not be able to get the information because maybe the engineers aren't there anymore, or they just simply don't know. And you've got to make some decisions without good information. So the sort of cryptography idea where you sit there and you write down some assumptions, and then you go do some analysis on the basis of those assumptions, doesn't quite work if your assumptions are really just some guesses and poorly written documentation and conversations with people. And this is just one area. You're building a chip, you've got to worry about how are your scan chains going to be done, and can attackers take advantage of those, or clock generators, or synthesis tool optimizations. Like, synthesis tools love to optimize away your countermeasures. Voltage regulators and what those mean. So these are all things where I could easily spend a couple of days talking about just the issues that you've got in dealing with security around buses or power on sequences. And again, so the abstractions don't serve us well here. Now, there is a different place where abstractions are your friend, which is when you're trying to figure out how to fit your security system into a broader context. Often you want to work at abstraction boundaries. Like one of the reasons that SSL was so successful is that it sits nicely at that abstraction layer of the programmer using a socket interface and what TCP provides at the networking layer. And if you look at a VPN appliance, likewise, you've got this concept or this interface of an Ethernet connection coming in one side and Ethernet connection coming out, and you've got this appliance that can sit there. And because you have these existing standards and definitions and abstractions around how that works, is an opportunity to insert something in the middle and provide some security benefits. So the next area is around trying to reduce defect rates. And usually if you look at the way hardware or software is built, there's somebody who's kind of the architect, and then it gets handed to implementation, and then there's a verification team, and then you release something. And the ways that I've had to organize teams in order to reduce defect rates is to really make verification be the main thing that drives the design. So that means that as you're making design decisions, the question of how testable is this and what are the risks is the primary decision factor about how you architect something. And this has some other benefits because in terms of the actual costs, both in terms of the number of people and the amount you pay the people, verification is the largest driver of cost. You have way more people doing verification than you do doing architecture or even implementation. One of the things that really helps in this process is requiring really precise specifications. So that means making it really clear what the state is, what the computations are, what the assumptions are. And one of the properties that you can sort of look for to see if you're doing this well is that when an issue is found during the development process is whether it's really clear which layer that issue exists at. So if you come up with a bug and it turns out that it's kind of diffuse across the architecture, which was vague, the implementer made some assumption that was consistent with the spec, and then it kind of had some implication later. That's an example where you've failed to have precise definition about what you're working on. Even to things like how do you build a state machine? Do you have lots of branches or do you make it be very linear? What are your coding standards so that you can reason about the code? You can have tools that you can build that will be able to parse the code and understand it and make some kind of assertions about it. If you kind of let engineers go do what engineers are going to do, especially ones that aren't used to security, you're going to be unable to do a lot of other things downstream that you'd want to do. Simple interfaces, so the approach where you have a mode where you're loading data in and doing nothing else, one where you then run a transaction and you're sealed off from the outside world and something goes wrong, you might just delete all of your state. So you're kind of sort of load, run, output. Reduces a lot of complexity about the kinds of things that might go on, lets you do things like countermeasures to fault attacks because more effectively because you're, again, not doing anything kind of interactive with the outside. It doesn't work for every kind of an application, but it lets you reduce risk in some. In terms of tooling to be able to reduce risk, having tools that work across some of these stages in development or abstraction layers. So tools that can, for example, start with understanding what the flip-flops are supposed to be in the design based on the specification, and then look all the way at the final net list and say, okay, do I have the same number of flip-flops as I expected? And if I have a different number of flip-flops or they're holding different state than I thought, plus or minus inversions, then something unusual has happened and you want to dig into it. Another example is like the question of if I take my final design and I analyze transactions where any individual wire in this is at a defective state, do I find any surprises in terms of where the failures are, what was caught, what was not caught by my architecture? This is not just a question of the design. Again, we're talking about building systems for real people. So what happens in and after manufacturing, how keys are loaded, you have many stages to this process, all of which need attention from the security engineers. This goes back also to this problem of collapsing abstractions. There's a lot of things here that are just hard. Talking about earlier about why you might not want to work on practical things and just go think about theory. This is probably the place where things just get the hardest. You're constantly afraid of these invisible failures. You've built an RNG, it looks good in the first part, but how do you know that the next part that was manufactured or the billionth part that's manufactured after the manufacturing process has changed a bit is also going to provide the same entropy that you expect. Fault attacks and side channels are also ones where you could say, okay, I've got some characterization of what the leakage channels might look like, but that really doesn't give you proof that there isn't some better analysis tool or radio or some technique where somebody can collect more information from this than you expected. High-risk complexity elements, anything with pointers in software, for example. There's also this constant fear that you've made some wrong assumption or some surprise. If you were an engineer who didn't know about timing attacks and then some, 22-year-old comes along and presents a paper about it and you were vulnerable, it wasn't your fault, but you've made a wrong assumption here about the system that you've produced. And trying to figure out, okay, what are these wrong assumptions that I'm making? Again, it's really hard. It's nearly impossible to reason about because you're trying to reason about the things that you have absolutely no experience with. There's also just a lot of personal stuff. Raise your hands. Anybody here planning to be a specialist in verification of security hardware? One or two. Okay, awesome, awesome. But of the number of people that I would need to hire for a security team, I need way more of you than people that want to go design stuff. So we have kind of a problem here. So you two are going to be the ones that everybody's going to want to hire. But others are going to somebody's got to do this work. So you may be taking people who don't understand security and trying to train them, or taking people who understand security, train them in security, or taking people who understand security and learning some of these problems. But verification also isn't as glamorous as going and designing stuff. So it's quite difficult to do. You also have the problem that the things that reduce your defect rates are also the things that get the most impacted when schedules slip. So you've got some ship date, and if you have some late change because the foundry decided that they wanted to use a different process node because there was availability at that, and it's a little bit cheaper, suddenly you have these things that have shifted on you. And if the end date doesn't change and things run late during the design process, the verification team is the one that traditionally gets compressed. And there's no magic answer to this. I mean, if you think about deadlines, how productive are you? You've got all of this work that gets pushed right at the end. If that's just you doing a paper, fine. But if it's some entire verification team whose job has been compressed like that, they're just not going to be able to do as good a job. This also is somewhat alleviated by making verification be a key part of the design process, because they're involved all the way through and active, not just at that final phase. But it still becomes just a real challenge in practice. The last one, maybe the one where it's the most fun from a kind of academic research perspective, is this question of how do we build architectures where we can actually survive defects. So earlier I talked about what's the probability that we have 0 defects in a system. And for many applications, you're just not going to be able, given the requirements that are placed on it, to get that probability good enough that you can ethically go to Alice and say, go trust the system with your life or your money. So we have to be able to survive defects. How do we do that? And there's a bunch of strategies. Redundancy is the one that works in many areas. If you look at, the airplane that I flew to India on, that plane would be colossally dangerous if there was no redundancy in anything. If every single, there's only one pilot, only one engine, only one person checked whether the right amount of fuel had been loaded, and they weren't allowed to use a calculator, and ... you come up with an environment where the plane could conceivably fly, but you wouldn't want to get onto it. So how do you build systems that have real redundancy in them? And sort of one set of philosophies and approaches here is around having, especially in hardware, diverse, mutually untrusted blocks. And this kind of starts to look like MPC, but for bugs. So, kind of bug-resistant computation. And the reason this is kind of different from MPC is when I see people saying, okay, I'm going to go do MPC, what they'll often do is they'll go take a whole bunch of different computers running the same complex buggy software with the same vulnerabilities and think that there's better security from having split this computation apart, but actually added a bunch of complexity. And if they're all vulnerable to the same thing, you haven't really reduced a lot of from that exposure space. But getting bug resilience, again, is something that these kind of mathematical approaches can achieve, but it's not necessarily been the philosophy that's been underpinning a lot of the research. In the places, though, where I've done this, it's worked really well in practice. Like, so a lot of my company's solutions for pay TV, there would be a chunk of hardware that we would build that would go on the chip. Within that, there were there was generally a design requirement that, except for the few things where we couldn't do it, there should be no single points of failure. So the verification team would be allowed to say, okay, if the state machine here is circumvented by an adversary, can I break the security? If the answer is yes, that's a showstopper bug. And then when the actual chip was fabricated, there would be the piece that we designed, and then the piece that the sort of main system integrator would build that also had security in it. And the key would be a function, hash of those two. And if either was broken or if either was malicious, the other would be able to enforce the critical security rules. So that meant that there was no reliance then on either company to do the right thing or even to be ethical. And some of the concerns around this business were that some of the security vendors were acting unethically. So within an individual block like your state machine, you can do running hashes of state. You can do things that will maybe not give you full redundancy across the overall computation, but make it so that a particular piece that's at high risk has something that's being able to check to make sure that it works correctly. The model here is generally one where you assume that you can assume that the digital logic will operate correctly or it's a catastrophe. So you don't really think about, okay, we're going to have 6 out of 8 participants all working correctly. Well, either they all work correctly or you should shut down. But the question of how do you survive a scenario where various combinations or parts of the hardware are misbehaving is the objective. I don't have a good answer to the question of how do you model the risks of common flaws against different parts of the design. And this is one of the things that you spend a lot of time just worrying and stressing about, that if you've got 2 things that are doing the same computation, did you make the same error in both? One trend that's really exciting here, though, is that transistors are getting cheaper. So if you were to go back 20 years and say, okay, could you put 15 different logic blocks onto a big ASIC that were each doing a different piece of a computation, somebody would say, well, no, it's going to cost too much money for the transistors. If you look now at the price of transistors, they're essentially free, especially if you don't need any I/O pins or special logic blocks for things like fuses. So if you can do things in hardware, even putting multiple microprocessors onto a die really doesn't add a lot so long as they're small and simple, which they're going to be because you want them small and simple so you have a chance of being able to get the bugs out. Another piece of surviving defects is limiting the consequences of things when they do go wrong. So limiting, compartmentalizing, limiting blast radiuses. Software, the first thing you want to do is to kind of get memory safety so that a bug in one piece of the code isn't automatically going to give somebody a pointer that can compromise everything in that process address space, and to separate things into different processes. You see browsers, for example, doing a lot of this today. In hardware, doing a full, complete reset of all your state between transactions is another example where you can limit consequences. Like if you kind of imagined an old school computer from 20 years ago, I could turn it on, do a calculation, turn it off again, and be pretty confident that things left over from that computation wouldn't affect the next one. Yep. Okay, I'm almost done here. So being able to update software, system built for Blu-ray that can do that, or you just punt to the lawyers. So a bunch of business aspects here that make it even harder than just the technology ones. And then kind of wrap up, kind of going back to our Alice again. As we go toward practice, this abstraction of Alice starts to break down, and it becomes actually counterproductive. We have actual organizations, users, customers, including their aims and their impact on the real world. And my goal for cryptography is to make the world better by improving information security. But the organizations willing to pay for cryptography are all over the moral spectrum. And I would highly recommend that all of you look at Phil Rogaway's paper and his 2015 Distinguished Lecture. He said a lot of the things that I would have said if I was as smart as him and as if he hadn't done that. So really recommend that. But when I look at projects, I see these narratives designed to distract. And I'm going to be pretty bold here. You see surveilling terrorists and major criminals. That does not include selling spyware to authoritarian governments to spy on journalists and opposition politicians. That is just simply a lie when somebody says that. Entertaining sports fans does not mean getting them addicted on gambling and taking their money from them. Serving the people, if you're a politician, does not mean mass surveillance. It does not mean censoring the past. It does not mean using fear to prevent criticism. It does not mean being a bully. And revolutionizing finance does not mean Ponzi schemes, speculative bubbles, taking money from people who've been tricked into thinking that cryptocurrency is a path to riches. And when you look at where the money goes, or you look at what the ultimate goals are, you have to really look past those messages, because somebody will write you a check. That doesn't mean that they're going to do things that are going to make the world better. And some of my most important decisions were ones to not do projects. So the thought exercise number 2 that I'm going to encourage everybody to think a bit about is, what projects and organizations do and don't align with your values. But to wrap up, though, I'm just hugely optimistic for cryptography's future. The world security challenges are huge and growing. Cryptography is the most effective tool that we have in security. And there's just huge potential for improvement. And so just even little small expansions in how cryptography can be deployed usefully in practice can just have a huge positive impact. And I hope that you will help with those. Thank you.
Thank you, Paul, for a very interesting talk. So we have a little bit behind the schedule, but I want to keep the Q&A session. So please ask questions. Yes, please.
Thank you for this really interesting talk. My question is maybe a bit specific, but I think it points to a broader point. You talked about this TPM stuff and that you're really not convinced about them. And I get the point that they're complex, and I'm not working in this field, so I agree with that. But what would your suggestion, so what do you think is better? Because doing everything in a complex Intel processor with speculative execution and timing stuff is not better, right?
At a very high level, I think we need to have a bit of like the big little architectures. If you look at, for power, we have different processors for fast and different processors for efficient. We need different processors for security as well. And they need to be built with security in mind, where the people working on them aren't stuck with kind of legacy compatibility requirements and performance constraints and all of that. And the question of what should those look like is a really interesting research question. What should the memory interface look like? What should the bus interfaces look like? What should the, et cetera. And it's a problem that is not going to be solved by the microprocessor people. They don't understand security. So the question of who is going to come up with that architecture, it's going to be somebody in this room, not somebody who's going to come in from the outside galloping in with an answer that meets the needs of cryptography.
Okay, thank you.
The question? Yes, please.
Thank you, Paul, for the wonderful talk. I want to ask a question about something you mentioned, that if we...
That's quite a question.
So you mentioned we can, if we add the redundancy, where we simply replicate the software, probably adds more bugs than it solves it. But okay, there are many, right now there are many industries which are actually doing distributed trust, decentralized finance, and all this kind of stuff. Have you looked at those and what kind of issues those companies are facing? They're definitely facing the software issues that you mentioned, probably many other things, because it involves cryptography, distributed systems, probably incentives and all of that stuff. So what are your experience with, have you worked with these companies, and what do you think about their future and all other things?
I mean, the question of who makes money and what's effective, there's some complexity around that. I'm not going to talk about specific companies here. My experience is broadly with things like MPC and threshold systems in practice hasn't been very good. Like, I've been part of some of the quorums for managing keys, and the process often ends up being the person who's kind of the manager of it all calls you up and says, okay, time for a signing ceremony, go get the thing out of your safe. And half the people can't remember what the combination to their safe, and then they get the thing and they all go to the room and there's a hash on the screen of the thing you're signing and you don't know what it is. And I remember doing an evaluation of one and realizing that all of the hardware was the same hardware, the same software, the batteries manufactured on the same day and were going to expire on the same day. And you can kind of predict how these things will work. They look nice from a paper cryptographic perspective, but the cryptographers can't just stop at the algorithm abstraction. They have to go down and say, okay, what's this going to look like in the field? What is the user interface going to look like? What's the hardware going to be? And a lot of the companies that I have worked with as an advisor struggle with this. You've got people who understand one level really well, which is maybe the math, and are coming from an environment where they haven't been exposed to a lot of the kind of practical engineering constraints, and tend to have hired people who are like them. You know, three friends get together and start a company and they all had the same PhD advisor. You're going to have a lot limited perspective on how to solve some of these. So I think when you look at a particular company and ask the question of, okay, what's the chance they're actually going to have vulnerabilities that circumvent the objective, and what's the perspective they have about the end users and use cases? You know, things look good there. You have I'm optimistic about how that will turn out. Often there's some challenges though that will come along.
Thank you.
One more question. So maybe this is the last question. So please.
Thank you for your talk. My question would be, in the modern capitalist world, how do you even imagine security being profitable and, you know, prioritized?
So in which world do you say?
In the modern capitalist world, how do you even see security being prioritized? It doesn't seem like security is something that is significantly profitable. It's usually possible to cover for the losses by having some kind of insurance, by having extra money. So no one actually cares on the big scale, and DeFi is another example of that. So.
I mean, this global spending on security technologies right now is in the sort of $100 billion range, and the losses are vastly more than that from compromises. So there is a big market for things that really work. Now, there's not a market for a big pile of code that somebody wrote as an academic project that doesn't actually solve somebody's problem. So this, as I see it, the issue is not around, is there a market? There is a big market. It's more the difficulty of taking these tools that we have that are defined very well up to a particular point, but then there's this kind of chasm of uncertainty about how to connect that to real world problems. And that means, you know, spending time with a customer, understanding, okay, you've got a database administrator who's used to SQL databases and is standardized in a particular thing, and you've got this cryptographic design, and they can't map it to their experience, so they don't adopt it. You know, it's easy to say, well, that was a market breakdown, but I would actually say, no, that's a case where the technology and the market need don't quite align, and you've got to do some more work on that. And that work is really, really hard. That's a big part of why my circles were so small, and why I think evaluations are a great way to kind of get into the business of working on security problems, because you go in there and you see who the people are, how they operate, what their systems are, what their procedures are. But companies want to reduce their risk. They were willing to spend a lot of money to do that. The question, though, of really what will reduce that risk, when you're totally honest about the challenges of what you're providing, ends up being just very difficult.
Okay, so I believe that you have many more questions to ask, but I think Paul is happy to answer offline.
Yes, thank you so much. Really appreciate.
We have. So thank you for the lecture.
Thank you, Sasaki-san. I really appreciate it.
So, yeah, everyone, please once again thank Paul Kocher for the nice talk. Okay, then okay, so yeah, so that's the end of the session, and please next is like a track switch.